So, my dear friends, this is Prof B Oza again. We are starting a new series today that is on generator protection. You see, one has to remember that we are talking about large generators. We are not talking about 1 kVA, 10 kVA, 5 kVA, 100 kVA generators. We are talking about at the most say 60, 70 megawatt, 120 megawatt, 210 megawatt, 500 megawatt, 660 megawatt generators. So we are not talking about small generators. Small generators can't be protected by so comprehensive scheme. In 1993, when I was in GB, the tender of relaying was of 4 crores of rupees. You can imagine. We are telling that we can spend 5% of the cost of equipment. So if I'm spending 4 crores, then 20 times that, 80 or 100 crores, must be the cost of generator, 210 megawatt generator at that time. Now it is very high. I learned that it is about for 660 megawatt, 2 generators, 2 into 660 megawatt. Somebody just before few months commissioned, it is 1875 crores, 1875 crores, no doubt, including boiler, turbine, auxiliaries, switchyard equipment for that generator, etc. But anyway, what I'm trying to tell is we are talking about large generators. And what are the faults and abnormalities in large generators that we would like to discuss? We will discuss slowly. There will be around 8 to 9 tutorials on generator protection fully. So we will be going slowly. This particular tutorial should not be more than 30-35 minutes. Because you learn slowly, you read some things, digest that and go to the next. So fundamentals of generator protection. We will be talking about concepts. Before we talk about generator protection, we should know how it is connected. You see, for transmission line protection, we have discussed that if the fault occurs in the line, if it is in the interconnected system, then breakers at both ends have to trip to isolate the faulty section. That is all. Breaker trips, fault is isolated. Unfortunately, and so to say, so because the generator protection is complicated, is the reason that tripping of 52G, 52G means generator breaker. If it trips, fault is not isolated. We are talking about fault in the generator. And say in the unit system of protection, non-unit system is also existing, but in unit system of protection, it is like this, as shown in the figure, that there is this 15.75 kV 210 megawatt generator. 15.75 kV is one typical figure. It can be 22 kV, 500 megawatt also. But this generator is connected to GT, generator transformer. A power transformer associated with generator is known as GT. There is no breaker between generator and GT. There is no breaker between generator and GT. Because you see, if at all you keep a breaker, the main thing is its breaking capacity has to be very high, because it is the only subtransient reactance, because you have to take care of the worst reactance, and subtransient reactance is 20%, very low. Therefore, the breaking capacity of the generator required would be very high. One thing. Second thing, that the 15.75 kV 210 megawatt, usually 0.85 power factor is the design power factor. The current calculated is 9050 amperes, roughly 10,000 ampere. You see, so the rated capacity of the breaker has to be 10,000 ampere. So there is no breaker between generator and GT. There is no breaker between generator and UAT also. You can see that on both sides of generator there are UATs. It is known as unit auxiliary transformer. A and B for flexibility. Flexibility means if some auxiliary is out of order, then you can run the generator at reduced power, but generation will not completely stop. Because you see, if it is a thermal power plant, and if generator stops means turbine is also to be stopped, and then boiler also has to be stopped. Once you stop the boiler, it will start cooling down. Then to bring back the generator to resume the generator to infinite bus is not a child's job. From completely cold condition of the boiler, it takes 7 hours to start the generator. So generator in thermal power plant, which we show by simple circle and SC sign, is not that easy. And at least in one shift, some 10% persons are working. In 3 shifts, 30 persons are working only in control room. I'm not talking about turbine floor. Uh, there are 4 or 5 floors. Many people are working. It's a big business. Generation is a big industry. You see, it's a very big industry. So one has to understand that generation is a complicated phenomenon. So it's not only fault in the generator. See, it's not fault in the generator, but fault in generator transformer is also a fault in the generator because there is no breaker. Fault in UAT is also fault in the generator. So anywhere the fault occurs, tripping 52G is not enough because generator is running, it is generating. So it will feed its own fault. It will feed its own fault. One thing. So second thing, after 52G, you have to trip the field breaker. You have to trip this field breaker, which is supplying DC current for producing flux. Fleming's right hand rule, you see. First finger is flux, thumb is torque. Torque is given by turbine, steam turbine. Right? And the electricity voltage is induced. Voltage is induced, and if you complete the circuit, it will give current to the consumers. So try to understand that when generator is generating 210 megawatts, it is not giving 210 megawatts to infinite bus. 10%, 21 megawatt, roughly 21 megawatt is eaten away by generator itself. Because you see, for running the turbine, you have to run the boiler. And for running the boiler, first of all, you need the coal. So where from the coal will come? Coal will come through railways. So that coal is to be unloaded. You cannot unload by soil. You see, you have to use a wagon tippler. Complete wagon is made upside down. So one big 415-volt induction motor is working to topple the wagon tippler. Right. Then that coal that is coming has to be crushed because that coal you cannot feed to the boiler. So it has to be crushed first by crusher. So in primary crusher it is crushed to certain extent. In secondary crusher it is crushed further. And then in coal mill it is powdered. It's like a face powder. Because you see then only it will burn fully. We have to use complete energy of coal, potential energy of coal. And coal can burn in presence of oxygen. So you have to feed oxygen and therefore you have to run primary air fan. You see all these things. Primary air fan is 1250 kW induction motor. It is a 6.6 kV motor. It's a large motor. Then you have to feed water because water is converted to steam. Ample amount of water. And so ample amount of water that much water you cannot take once and throw it away. You have to recirculate the water again and again. That means water will go to steam, then steam becomes water, water will become steam, steam becomes water. That is the thing. And therefore, the water has to be made to reach up to 55-meter height. 210 megawatt boiler is 55-meter high. There at the top there is boiler drum and boiler feed pump is at the ground floor. It rather serves water to boiler drum at 170 kg per centimeter square. At 170 kg per centimeter square, roughly 275 degree. It is water, my dear friends. At 100 degree, water turns to steam. But here, because it is 170 kg per centimeter square, it is yet water. So, when there is a fault in the generator, GT or UAT, you have to strip 52F. But 52F you trip means turbine does not drop. Turbine is running and therefore fault means some flashover somewhere. So that fault will be fanned. That means that flashover will be made more intense because the generator is running at 3000 RPM. I talked to my student friends that if you cannot appreciate 3000 RPM, because usually students are hearing, they are hearing the words. जैसे कि न्यूज लीडर बोलती है ना, there is a war between Ukraine and Russia and 30 lakh people are died. So 30 lakh is a number for us. मगर जिसका बेटा मर गया वो माँ के लिए तो 100% था वो. तो वो हम नहीं समझ सकते. We simply hear figures. 3000 RPM, if you cannot appreciate, let me convert to RPS, revolutions per second. 3000 divided by 60, it is 50. Try to take out the pen from your pocket and manually rotate it at 50 revolutions per second. Here, 300 ton of mass is revolving at 50 revolutions per second. It is a two-pole machine, bipolar machine. So, the fault is being fanned. So, turbine has to be stopped and therefore you have to close the steam stop valve. Immediately turbine has to be stopped. You have to close the steam stop valve so that turbine stops. So boiler, once turbine stops, why should you feed steam to turbine? So boiler has to be stopped. My friend was chief engineer at Tokai and he told that the record breaking time within which they could restore the boiler, or rather they could uh, give the boiler, resume the boiler to the infinite bus, you see, was 1 hour and 45 minutes, roughly little less than 2 hours. Because the boiler furnace temperature is 1150 degrees centigrade. If it goes down by 100 degrees centigrade also, then you have to work once again. You see. So, when generator trips, when there is a fault in generator, GT or UAT, you see, some 48 events occur. Generator breaker trips, generator field breaker trips, turbine stop valve closes, boiler trips. Boiler trips means boiler is not an electrical equipment. Boiler trips means its flame will be quenched. No flame will be there. Boiler trips. All 6.6 kV auxiliaries, 415 volt motors, everything will come to halt. Complete power plant will be silent. And it's a very big thing. The chief engineer has to report to 7 persons in the state that one of the generator has tripped. And even if he does not say, the load dispatch center knows that the generator has tripped. No doubt, if the fault occurs, nobody can do anything. Generator has to be tripped because otherwise there will be crores of rupees of damage. So, protective system has to work. But then what I'm trying to tell is it is too complicated. Some 48 events occur. If we go further, UAT, unit auxiliary transformer, is feeding unit auxiliary bus A and bus B, right? Two buses just for flexibility. I have shown one induction motor there, 6.6 kV unit auxiliary motor is shown. That is, you see, there are many auxiliaries. As I told you, boiler feed pump, PF fan, ID fan, FD fan, condensate extraction pump, circulating water pumps, BFP. You see, many auxiliaries there. For one 210 megawatt boiler, there are three BFPs. Two are running, one extra. Six coal mills. Four are running, two standby. But if coal is not good, sometimes five are running. You see, there are two PF fans, there are two ID fans, there are two FD fans. So one ID fan is on bus A, one ID fan is on bus B. I have not shown all motors. This one motor is just a representative, but there are many motors, many 6.6 kV motors. One thing. Second thing, then there will be 6600 by 415 volt UST, unit service transformer. Because many auxiliaries are 415 volt motors. The air preheater motor is 415 volt motor. All, so to say, the bearing cooling motors are 415 volt motors. Because in bearing, lubricating oil has to be cooled. All PFN is running at very fast speed. So there the lubrication has to be done near the bearing, otherwise bearing will be spoiled. That lubricating oil becomes hot. So that is taken out. It is cooled. Then once again, so that circulates. So for circulating the PFN bearing oil, you have to use one motor, that is for 15 volt motor. For BFP also, that lubricating oil has to be circulated, and for that one, for 15 volt motor has to be run. So you see, if you see from fractional horsepower 0.5 HP to 4 megawatt, that is roughly 5000 HP. BFP motor is the biggest motor, 2 megawatt in 210 megawatt plant. 0.5 to 2 megawatt, there are 500 induction motors running in power plant. That is why I am telling that it is a big industry, right? So for converting to 415 volt, you need UST, roughly 2000 kVA, 1600 kVA. Right? It's a distribution transformer like thing. UAT is 15.75 kV to 6.6 kV. It is converting to 6.6 kV because they are all 6.6 kV motors. So unit auxiliary transformer is 15.75 to 6.6 kV. This is 6.6 kV to 415 volt. And then it will feed many 415 volt power control centers and motor control centers. Right? So you can see that is there. Third important thing, that when fault occurs, the generator will stop. So now you have rectified the fault and you want to restart the generator. For that you have to run the BFP, you have to run the PFN. Everything is on 6.6 kV unit bus, but there is no power there. So 6.6 kV bus always has to have a power. It cannot be powerless. Not for a moment. So as a part of class A protection, we'll see, as a part of class A protection, from station bus to unit bus, there is a tie line and tie breaker is there. Tie breaker is normally open because the power is fed from 6.6 kV unit bus. But then when unit stops, power is fed from station bus to unit bus. Tie breaker closes as a part of, automatically as a part of class A protection scheme. This is very important. Tie breaker on both sides. So obviously tiebreaker means tiebreaker comes from where? It comes from station bus A and B. Station bus A and B are getting power from 220 kV infinite bus because 220 kV infinite bus is getting power from all power plants in the state. So it will never be dead. It will be dead only if cascaded tripping occurs. And therefore, if cascaded tripping occurs, it takes at least 6 hours to resume power in the state. So cascaded tripping is a big incidence. Not only that area, but the whole world will be interested in the reason why cascaded tripping occurred. Because that reason should not be repeated. If you make a fault once, it is a fault. Second time, it is a crime. It is not fault. Right? So, this in 2012, in uh, northeastern grid and northern grid, eastern grid, power failure occurred. The report is of some 70 pages. It is available on Google. You can read. Why at all? The 22 states were affected. There was no power in 22 states. Complete blackout for some 5 hours or so. So, what is the reason? Everybody were interested. And the reason was purely power system protection. It was load encroachment, I told you while I was discussing distance protection. It started with load encroachment. One state can get power of some 100 megawatt or 200 megawatt. That was the MOU. But the other states started fetching more power. So that was the reason why the cascaded tripping initiated. And then it was followed by pole sleeping of generators and many more things. But this happens. Therefore, 6.6 kV unit bus gets power from station transformer, which is 220 kV by 7 kV, some 25 MVA. Station transformers are not many. In Ukai, there are 7 units, but only, I think, some 6 station transformers, so 5 station transformers. Station transformers are not the unit. It is not one per unit. It is feeding other units also. Because you cannot have many station transformers. It is costly. 25 MVA transformer to 20 by 7 kV is a costly transformer. So station bus A feeds the unit to restart. But it is not only restarting, my dear friends. It is also, there are many emergency auxiliaries which are to be fed even when the unit is stopped. Even when unit is not working. Say, APH motor, air preheater motor cannot be stopped, otherwise it will be damaged. It is kept running even if plant is not working. Bearing gear motor, you have to keep it on running even though the station has stopped, the generator has stopped. So this power that is received from station bus to unit bus, you see that power is used for running this emergency auxiliaries also. But that is not the only thing. There are certain station auxiliaries. Some auxiliaries are unit auxiliaries. Say PFN is unit auxiliary. PFN for unit A cannot fit to unit B. PFP cannot fit to another unit. ID fan, FD fan, CE pump, all are unit auxiliary. But coal handling plant. Coal handling plant is a station auxiliary. All 7 units in Manakbori. Now 8th unit also has existed. All units are fed by common coal handling plant. CW system, circulating water system, is a station auxiliary. So there are station auxiliaries also. So those station auxiliary motors are also big motors, like crusher motor is a 6.6 kV motor. Then the conveyor belt motor is 6.6 kV motor. So this 6.6 kV motor, as a representative, I have shown only one. You can see I have shown only one. But there are many. Then in 415 volt also there are 415 volt PCCs and MCCs. So you need, as you need UST, you need SST, station service transformer. So this whole thing, this whole business makes a generator, and fault in a generator, and to clear the fault in a generator is a big business. That one has to understand. Little lengthy, but this is very important. And this is not taught in any university. No university teaches. People teach differential protection of generator. People teach at the most field failure protection of generator. People teach at least 10 PS protection of generator. 2, 3, 4 protection and that is over. But in field if you go, there are many protections and student fails to understand these protections. So going further, my dear friends, going further, this is what I discussed. Yes, all these things I have discussed. The 210 megawatt power is generated by generators fed to 220 kV bus through 52G. 10% of power is consumed by auxiliaries. These auxiliaries are fed by UAT, and 6.6 kV unit auxiliary bus has to be kept live even if unit trips, because to feed to emergency auxiliaries. These all things I told. This is accomplished by closing a tiebreaker. That's what I told. And 6.6 kV station bus fits station auxiliaries like coal handling plant and CW system. That I told. And there are 415-volt motors and auxiliaries too, which are fed from 415-volt unit and station buses. All what I told. So with that, we see the major faults and abnormal conditions in the generators. What are the major faults? Failure of insulation of stator winding. So when we see further, we will see three things. What are the causes of failure of insulation? First, right? What are the causes of failure? Why stator winding insulation should fail? What are the possible causes? Because only if you know the causes, then you can do some medicine, no? Then you can do some remedy. Then consequences. If you don't remove that cause, what are the consequences? What will happen to generator? That is important. And then the last, protective scheme. What protective scheme you employ for that? Similarly, failure of insulation of rotor winding. Same three things. So these two are faults. These first two are faults. Others are abnormalities. They are not faults. That means current is not passing through undesired path. But these abnormalities damage the generator. Unbalanced loading, that is IR, is not equal to IY, is not equal to IB. And they are not 120-degree apart. It is not balanced. What is the definition of balanced loading? IR, IY, IB are magnitude-wise equal. Their vectors are 120-degree apart and phase sequence is RYB. That is, if you rotate the vectors in anti-clockwise direction, Y takes the place of R and B takes place of Y. That is balanced. If this is not, then it is unbalanced. Field failure. Mind you, field failure not of single generator. Field failure of the generator which is connected to infinite bus. Field failure is a very complicated phenomenon, right? And very few people can fully explain the field failure. Overloading of a generator, over voltage, generator voltage increases. Once again, we'll see causes, consequences, and protective scheme. Failure of prime mover. Prime mover fails. The prime mover does not run the generator. Loss of synchronism. The load angles of all the generators working in the system are different. It is asynchronous working of all the generator. So loss of synchronism affects the whole power system, not only a generator. But here we will talk of generator only. Power system we have talked of. That if power swing comes, which distance relay should operate, which distance relay should not operate, how to deal with loss of synchronism. And then there are many other things also. When system becomes unstable, you have to do load shedding. So load shedding itself is the subject by its own. Right? There is one full chapter for I can take full full chapter. I can take such 4 videos for load shedding. How to do load shedding. In what steps you should do load shedding. You should get to 2 megawatts. If you have to cut 10 megawatts, then you should cut first 2, then 2, then 2, or 4, 4 and 2, or 5 and 5, or 10 at a time. I mean, it is a complicated phenomenon. Load shedding itself. Load shedding, synchronism, all these are subjects by themselves. Everything we will not be able to see, right? Because we do not have that much of time also, and to that depth, probably people require to understand if they are manufacturing a generator or they are dealing with generating plant, they are operating the plant, they are maintaining the plant day and night, then they want to understand. Laymen may not want to understand everything. Overspeeding. Overspeeding is not a big problem for uh, coal-fired boilers because steam is a very it is not very thick liquid, uh, whereas water is so hydro turbine. The overspeeding is a problem. You cannot reduce the speed immediately. So overspeeding relays have to be used in hydro turbine. Under frequency is a big thing, the very big thing, because if the frequency reduces, you can reduce the frequency, take more load. See, load frequency curve is dropping. So if frequency decreases, you can take more load. So in earlier days, when generation was less and load was more, people were going up to 49.7. But then if you go to 49.7, the steam condenses in the last stage of LP turbine, low pressure turbine. And low pressure turbine over a period of time will be damaged. So if its life is 15 years, it will live for 5 years, so 7 years, or 8 years. So life expectancy of turbine reduces. So under frequency is a very important phenomenon. Nowadays, on all 11 kV substations, some 2 or 3 feeders are kept as they are auto tripped on under frequency. If the frequency is 49.95 or 49.94, they will trip so that load is reduced and frequency is maintained. So now if you go to power plant, I have seen, had been to power plant in 80s, and I have seen 49.6, 49.7, not 6, but 49.7 I have seen. Now I'm never seeing 49.7. It's always 49.97, 49.98 at the most. Low hogi to 0.02 low. High 50.01, 50.02. It will never be 50 or 50.5. You see, that is very important. Frequency, to maintain the frequency is very important. Otherwise, the generator will be damaged. System will be under problem, that is another thing. But the generator means not generator. Generator can run at any speed, but turbine will be damaged. You see, in many of the abnormalities, you will see that the turbine is damaged, not the generator. But then it is the same thing, no? After all, we are spending for the turbine also. So you have to, when you talk of protection of generator, you will have to talk of turbine protection, and you will have to talk of boiler protection also. You cannot remain without talking. So that is the reason why the protection of generator becomes quite complicated, and that complicacy we have to learn. Overheating. Why the generator overheats? So these are the major faults and abnormalities. And what protective schemes we employ? We employ differential protection, interturn fault protection, stator earth fault protection. You see, once we'll discuss, you will understand that stator earth fault protection is also very complicated. We are going for 100% state earth protection. That means the fault at the neutral is also detected. Actually, fault at the neutral is no meaning. Neutral is already at zero potential. But then we protect that too. So why do we protect? That is worth understanding. Very much worth understanding. Overcurrent and earth fault protection for small generators, not for large. Because differential protection is used, overcurrent and earth fault is not required. For small generators. Small generators means below 15 megawatts or so. You can use overcurrent and earth fault protection. No doubt you will have to use voltage controlled overcurrent relay because the synchronous impedance of the generator is always more than 100%. Therefore, the fault current is always less than highest rated current of the generator. Rotor earth fault protection, negative phase sequence protection, field failure protection, overload protection, over voltage protection, reverse power protection. As such, people do not use reverse power protection. Low forward power protection is used. It is not allowed to be reverse also. If forward power is less than 0.5% of the rated power, then the protection will work. Reverse power protection is also there, over and above low. There are two low forward power relays because low forward power protection is very important. All class B protections are routed through low forward power protection. What is class A, class B and class C, we have yet to understand. Maybe in the next tutorial. Pole slipping protection, backup impedance protection and under frequency protection. So many protections we will study in 8 or 9 tutorial classes of the generator. This is the first one. With that, my friends, I end this first tutorial. I just initiated what is generator protection. I just initiated how complicated it is going to be. So with this sentence, I end. Be realistic. Plan for miracle. Miracle does not happen. This life itself, this reality itself is a miracle. Your eyes are seeing. The person is dead. His eyes are not seeing. If you are living, you are seeing. If you are living, you are moving your hand. That person does not move the hand. Your whole life, you are walking, you are drinking, you are eating. आपके पेट में खुराक हजम होता है. The food is digested in your stomach. All these things are miracles. And people say that if you change something to something, एक चीज में से दूसरी बना दो तभी miracle है. That is not miracle. That is a game. This what God has given is a miracle. So be realistic. This reality itself जो आप है वही एक बड़ा miracle है. With that, I would remember adapt me that I am continuously on WhatsApp also writing to my dear friends. My student friends are my ambassadors. They should share this video to as many friends as possible. And if they find that somebody is concerned with this, say, generator protection now, somebody is working in this generator protection field, then if they hear this, they will get some clue. They'll be able to work better. So I would request everybody to share and see the video, hear the video, because the view hours are very important in YouTube. How many persons have viewed and for how much time they have viewed, that is very important. And this is nothing unimportant. This is very important and free of cost. So those who see this video, anybody in the world, known to me or unknown to me, if you find that this is really worth it, then please yourself, you see the video, hear the video, like the video, subscribe our channel, share to your friends. Please do these things. A that will be a payment in a way. You see, this is free of cost, but that will be a payment to adapt me. So please pay that, not from your pocket, not money, but in these terms you please pay us. So with that, my friends, thank you and goodbye.